Welcome to multiple choice questions. Two identical spheres separated from one another are charged to absolute potentials V1 and V2. They are connected together to share the charge. They acquire a common potential of A V1 plus V2 by 2, B V1 minus V2 by 2, C V1 V2 by V1 plus V2, D V1 plus V2. This is the question. So these are two identical spheres at potentials V1 and V2. You know that capacitance C equals Q by V or Q equals C into V. Since the spheres are identical, capacitance will be the same. Therefore, charge on the first sphere Q1 equals CV1. Charge on the second sphere Q2 equals CV2. Now, when the two spheres are connected together, so that they can share charges. They share equally. Q1 and Q2 are the initial charges on the spheres. So total charge on both the spheres will be Q1 plus Q2 or CV1 plus CV2. That is total charge to be shared. This total charge is shared equally since the spheres are identical. So after sharing, charge in one sphere will be Q1 plus Q2 by 2. Half would go to one, the other half would go to the other sphere. So total charge after sharing is still Q. And total capacity is twice the capacitance of one sphere because they are connected and the capacitance of one is C. So capacitance of the two as a combination is 2C. So common potential after connecting or after sharing V equals Q by V, total charge by total capacitance. That is Q1 plus, this is Q1, Q1 plus Q2 by 2C. Q1 is CV1 plus CV2 by 2C. C would go. Final answer is V1 plus V2 by 2. That's all. The electric field just outside a spherical shell of radius capital R and charge capital Q in terms of charge density sigma is A sigma by epsilon 0, B sigma by 2 epsilon 0, C 0, D 2 sigma by epsilon 0. So, we know that potential, electric potential at this surface or at a point very close to a surface of a spherical shell is 1 by 4 pi epsilon 0 into Q by capital R, where capital R is the radius of the sphere. Say intensity is Q by R square. not potential, intensity, electric field. Electric field means intensity. E equals 1 by 4 pi epsilon 0 into Q by R square. This can be written as Q by 4 pi R square into 1 by epsilon 0. Now Q by 4 pi R square is nothing but Q by area of the sphere. 4 pi R square is area. Q by A is the charge density sigma. So E equals sigma into 1 by epsilon 0, or E equals sigma by epsilon 0. This is the answer. Or you can use Coulomb's theorem directly. Potential very close to the surface of a charged conducting body is sigma by epsilon 0. Here is another problem. A dielectric sphere is introduced into a uniform electric field of intensity E. How will the field be affected at points A, B, and C? Choice A. Intensity remains the same at A and C, and will reduce at B. Second choice. Intensity reduces at points A, B, and C. Third choice. Intensity increases at A and C, but decreases at B. Fourth choice. Decreases at A and B, and increases at C. So this is the figure. Uniform electric field. This is a dielectric sphere. Points A, B, C. What happens to the electric field at these 3 points? That is the question. See, by induction, charges will appear on this, or what, dielectric polarization. Dielectric polarization, induced charges will appear on the sphere. The field is shown to be directed in this sense. That means field creating charge, positive charge of the field creating system will be somewhere here, and negative charge, negative field creating charge will be somewhere here. So by polarization, negative charges will appear here and positive charge will appear here. Now at the point A, there are 2 fields now. One is the original field E, like this. The other is the field due to the induced charge, this minus. This is minus charge, so direction of the field due to this charge is towards this. Field is always away from positive charge and towards negative charge. So induced intensity due to the this induced charge, E dash, is towards this charge. So that E and E dash are in the same direction, and the field at A will be E plus E dash, or field at A increases. Same happens at C. Original field is E in this direction. Charge generated due to polarization, that is plus here. So E dash is also away from this. In effect, E and E dash are in the same direction. So field at C is E plus E dash, or field is increased. Then field at C is inside point here. E is in this direction. E dash is in this direction, from this plus to this minus E dash. So field at B is E minus E dash. or feel that the point B is reduced. Another way, you know that due to polarization, intensity inside a dielectric material decreases. So feel that A and C increase in intensity, feel that the point B decrease. The choice is C. C increases at A and C, decreases at B. That is the answer. A point charge, capital Q, is there at a distance smaller from the center of an uncharged conducting sphere of radius capital R. What is the potential of the sphere? A. Q by 4 pi epsilon 0 into, within brackets, 1 by small r plus 1 by capital R. These two are within brackets. 1 by small r plus 1 by capital R. B. Q by 4 pi epsilon 0 into, within brackets, 1 by small r minus 1 by capital R. C. Q by 4 pi epsilon 0 into small r. D. Q by 4 pi epsilon 0 into capital R. Small r and capital R are in the denominator. So C is Q divided by 4 pi epsilon 0 into R. Small r. R is in the denominator. The fourth is Q by 4 pi epsilon 0 into capital R. Capital R is in the denominator. Now this is the point charge. This is an uncharged, initially uncharged sphere, conducting sphere of radius capital R. Now what is the potential at this sphere, or potential of this sphere? That is a question. Now you can think it in two ways. One, potential V of this sphere is potential created by Q on this sphere plus potential created by charges induced in the sphere. The first one is potential created by this point charge on this sphere is same as potential of Q produced by Q at the center of this sphere, which is nothing but 1 by 4 pi epsilon 0 into Q by R. Potential due to the induced charges will be 0 here, because this is plus, this is minus, because induced charges is negative near the inducing charge, and opposite, if it is plus, charge, induced charge near, facing this charge near surface will be negative, and at the far surface it will be plus. So these two charges produce zero potential here, because potential of this is plus here and potential due to this is negative here. These two charges are at equal distance from this point being the center. So net potential due to the induced charges will be zero here. In effect, potential of this sphere is potential due to Q plus potential due to induced charges. Potential due to Q is 1 by 4 pi epsilon 0 into Q by small r plus potential due to induced charge is 0. Or the answer is Q by 4 pi epsilon 0 into r small r. That is the answer. Or you can think it in another way. Potential of the sphere due to Q, you can reverse the situation. You think Q to be given to this sphere, and potential as you find potential due to a uniformly charged sphere with the charge Q, at distance small r from its center. That is V equals Q by 1 by 4 pi epsilon 0 into Q by R. Because potential charge given to a spherical shell or sphere is equivalent to a point charge placed at its center, or potential due to a sphere, charge sphere, is equivalent to potential due to a point charge at the center of the sphere. Thank you. A spherical surface of radius capital R is imagined in a uniform electric field of intensity capital E. What is the electric flux entering or leaving the spherical surface? A. Choice: E into 4 pi r square. B. E into pi r square. C. E into 2 pi r square. D. E into 2 pi r. This is a spherical surface of radius capital R. This is imagined to be present in a uniform electric field of intensity E. What is the total flux entering the spherical surface or leaving the spherical surface? See, just you consider only one half of the spherical volume. Then E is perpendicular to the cross section, which is circle. So total flux leaving or entering will be equal to total flux associated with this cross section. Intensity is uniform, so the total flux is intensity into area. Here area is pi r square, this area. So flux associated or entering or leaving the spherical volume is E into pi r square. That's it. Thank you.